Hi, welcome to the video tutorial for two lessons really, both on rectangles. I think I'm going to talk about both lessons together because you could do one as a half-hour activity just to probe your class, just to see what they do, and then follow on with the next one, which does push them very far. And there's an interesting aspect in some of the thinking maths lessons where you open a door into the abstract world of maths where actually, mathematically, intellectually it's true, but physically it can't be true in the world. And I think sometimes it's nice to let them see through that door, to go through that door, and to see what they're thinking about, and to try and contextualize it into things that they're familiar with, but knowing that they're going into a very powerful world. Because I remember reading a book by a guy, I can't remember his name, but he was autistic, and he won a competition by reciting pi to 22,000 decimal places, and it was fascinating seeing how he thought about numbers. You know, and you've got the famous Indian mathematician, numbers are friends, and people see different things in numbers, and I think it's important to expose people to those type of thinking. So for many of these lessons, you can bring in aspects of maths that you're familiar with, that you like, that have inspired you, just to share that with the pupils, just to encourage them to talk and just encourage them to think. So this is two lessons on rectangles, and I would always, whichever one I'm doing, I would always start in the same way, which is tell them some story about my nephew in the kitchen, saying there's not many rectangles here, there's loads of circles, and say in the class, how many rectangles are in this room, in this classroom? There's normally thousands. Say, okay, rectangles are a very common shape, yeah? What I'd like you to do is get me to draw a rectangle. And if you don't give them any guidance and you just say it like that, they can't get you to draw a rectangle, because they'd say, draw two lines, and you do that. Whatever they say, you do it literally. So they'll say, draw a line. Draw a line and another line coming off it. Draw exactly the same on the other side. So you do that. You play devil's advocate, and it takes them ages to get you to draw a rectangle, till you then specify that is a rectangle, and they can name all the parts of the rectangle, the properties of the rectangle. At this point in the lesson, what you do is you show them this for about 2 seconds. It's in the PowerPoint. You show them that for 2 seconds, and you say to them, which do you think is the biggest? And then when you hide it again, you get them to talk, because you're focusing on a visual perception of size. Without mentioning area, perimeter, or any dimension, you say which is the biggest. So you can put that back up again, or let them keep arguing and say to them, okay, I'm just going to show you it again quickly. We've got A, B, C, D, and E. Which do you think is the biggest? And I want you to try and quantify it. So a lot of them will say, well, I think it's D. I think it's E. I think it's C because it's the fattest. So all of this without giving them the sheet. Then you can give them the sheet and say, okay, have you changed your mind? So they get this, and they then look at them, and they might change their mind and put them in order. So it might be, for example, that you have A, B, C, E, D. That might be the order that they choose. Okay, what I want you to do now is quantify which is the biggest. Measure the I want a measure of bigness. So what the pupils can then do is for A, B, C, D and E, give you their values for bigness. Now you can give them squared paper, you can give them rulers, they can use the fingers, it doesn't really matter, but you want them to give you a value for that. And often what you'll find is when the class come and write their results on the board, it's lovely, they'll say, just write your results on the board. You might have X, Y, and Z, X, X, and X. You might have most of the class have got one value. Some will be doing the perimeter, some will be doing the area, because you haven't specified what big is. And you're forcing them to argue as to what area, what perimeter is. And so for many pupils, if you've got a low ability group, you might want to spend time doing this and focusing on what is area, what is perimeter, how do we calculate it, because we're doing both at the same time to iron out the problems that have when you say we've done area, we've done, oh I've forgotten which is which, because you're saying which is the biggest, and then you could say does a bigger area always is area always bigger than perimeter, And you can have an activity of drawing shapes of how many rectangles of area 12 could you draw, how many different perimeters could you have. Read the notes, because the lessons in the notes are quite different. It gives an example of Islamic tile patterns. So there are several versions of these lessons that you could do. So that's the first part of the rectangles lesson. The second part I find absolutely fascinating. You would draw a rectangle on the board, and you would say to them, tell me something about that rectangle. Intuitively they know it's 12 because they can make 12 squares. You say, well, where did the 12 come from? Oh, it's 6 times 2 because that's 6 and that's 2. You say, okay, could we make any other rectangles of area 12? Any other lengths and widths? Oh, so we're going to have 3 times 4. We can have 12 times 1. Oh, we could have 4 times 3. We could have 2 times 6. We could have 1 times 12. You say, okay, brilliant. What I want you to do now is I want you to do something with these rectangles. So what the pupils get is they get a grid of squared paper, and you're asking them to draw these rectangles as if you squash them into the corner. So there's the 12 times 1, there's the 1 times 12, there's the 6 times 2, there's the 2 times 6, 4 times 3, 3 times 4. So some of them find this very difficult to do. So you're asking them to draw these rectangles and squash them in the corner and talk about any patterns they can see, what they notice. Then you say to them, okay, we're good at this now. What I want you to do now is I want you to draw it again, but do this. I want you to forget the rectangles. I want you to imagine the rectangles are invisible and all we can see is the corner. Okay? And then I want you to tell me what we see. And what should we call this? So a lot of them will join it up. And you say, well, what is it? Oh, it's a line. What is that? Where does the line come from? Oh, it's areas of 12. So it's the line, area, 12 rectangles. And you can draw other ones of these. You can pick a bigger rectangle and draw the same curve on the piece of paper. The bigger the paper you can give them, the better for doing this. You say, okay, I'm going to ask you, so where did this rectangle come from again? Oh, we drew the rectangles. So that's 1, that's 12, it's area 12 rectangle line. Okay, what I want you to do is I want you to answer 3 questions. You're going to think about 3 questions, but I only want you to answer one of them. We're going to have a discussion. And then do it in your pairs, do it in your fours, pick the one you can give the best answer to. And each question is ambiguous enough to lead to a quite interesting next step, to take with people somewhere interesting. As I said, open the door on quite an interesting world of mathematics. So you say to them, here's the first question. What does that curve actually mean? Where does it start and finish? And can we find, are there any other pairs of numbers? So you give them those 3 questions, write them on the board and say, pick one of them and come up with an answer. Think carefully about it. Think carefully, use your brains. Sometimes there's other meanings to these. Think about them, what could it be? And you can have the discussion. Sometimes children will take this very literally and say it starts there and ends there. There's no more pairs of numbers. And someone will say, well, what it means is it's just area 12 rectangle. Others will say something that you can go further with. And it's worth listening to what the pupils have been saying in the class. Some will say, we can have 8 times 1.5. That's 12. Oh, okay. So then we've got 1.5 times 8. And as soon as you've got that, you've got your foot through the door and you can start opening the door. Others will say it means, the meaning of this is it's the corner of rectangles. Sorry about that. It's the corner of rectangles. Okay. So what are these? They're corners of rectangles. And each way gives you an opportunity to slip in to getting and think about the infinite extension, the infinite subdivision of the line. So if someone says it's corner of a rectangle, you can say, well, okay, what's that? What's that? What's that? If 8 and 1.5 and 1.5 and 8, could we have more? And someone said, oh, you can have 24, and often they'll say times by 2, and rather than times by a half. You say, oh, 24 times by a half. Oh, all the way here. And often by now, you can go right to the end of the room and say, could it go here? You say, okay, so it means it's the corner of the rectangles. And so it goes here now and goes here now. And what starts to happen is they start to get into the rhythm of it. Well, actually, what's this? How many rectangles are there? Loads. How many's loads? Then they say things like, well, every point is a corner of a rectangle. Every point. There. And then, okay, how far could we go? 24 times a half. Could we have 48 times a quarter? Could we have 96 times? We could keep on. Well, what if, could we have 120 times 5.1? Could we have 1,200 times by 0.01? How far could we go? We could go, we could keep going on. Could we go to the moon? And this is where you're getting into the absurdity that these numbers can keep on going, but physically there isn't the material that would allow us to have a rectangle that narrow. But it's a sense of, you've got for the first time, they're really thinking about the infinite subdivision, the infinite extension of the number line, the fact that every point, the area under this curve is 12. But from this idea of a rectangle, and often I'll say to them, what have you seen that's different? I think sometimes you see something different and that takes you to a different place. And I think it's ideal for that, for them to reflect upon going into this abstract area of maths. There is another bit that I've seen done a couple of years ago in a girls' school in Jersey with some year 9s, where after they'd done that area, 12, they decided to do perimeter, 12. And that's when the girls started laughing and arguing. Because they could understand, they knew that that line, if it touched there, it wasn't a rectangle. And they could understand the sense of infinity, because they'd had some examples from some science teacher who talked about infinity. And at one point, I'm just going to show you this, at one point in the lesson, it might be worth talking about the cat in the hat comes back. In the cat in the hat comes back, the cat in the hat makes a mess, and he has a cat under his hat, cat A, who's half his size to help him. And what's under cat A's hat? Cat B. What's under C? And then you've got cats X, Y, and Z are really small, but what's under cat Z's hat? And he calls it a voom, but could you have a cat under his hat, and a cat under his hat, and a cat under his hat, and a cat under his... Yeah, and each cat is smaller than the previous cat. But what was really interesting in this lesson was the discussions that the girls had. I was observing several lessons, and I walked into the lesson, and the girls were talking about this. And what they could understand that, they could understand getting smaller here, but what they couldn't grasp around, get their heads around, was the fact that this line could get longer by a smaller amount every time, so never get to there. And they had so this is this whole thing about Greeks and rational, irrational numbers. And it was just lovely to hear them laughing about that and trying to argue to their peers about this line. They're saying it could get smaller by a little bit more, 0.001, 0.001, 0.00001. So it's getting longer, but it's not. It's getting longer by a smaller and smaller amount. Would it ever touch there? And there's a time where I think it's worth standing back and letting them just argue, letting them articulate thinking, because it is a joy and a pleasure. And the humour and the fun in these lessons is really, it just does you good.